All right, and I will share my slides. This one. All right, so this brown bag is about symbolic concolic execution and SMT solvers. I initially thought I was going to go heavier into specifics about implementing symbolic and concolic execution engines. It's going to be partly on that and partly on existing tools, and then also on a proof of concept I made that ended up being pretty cool. So yeah, that's what we will be talking about. All right, so symbolic execution, it's a technique used to model the execution of a program using symbolic variables. Now, to really kind of understand that, the opposite of symbolic execution is concrete execution, which executes the program with concrete, real values, basically just running the program. So symbolically, you model the variables and the actions within the program, and then you can perform introspection on them and develop constraints based on how the program executes. And I do also want to say I have used them before. I would not call myself as much of an expert at all as Julian is. So Julian, please, if you notice something wrong that I say, please correct me. If you didn't know, Julian did his doctoral thesis on this topic exactly. So yeah, odds are I will probably get something wrong. All right, so suppose we have this function here. It's got a few branches, so 3 separate branches and 1 variable. If we wanted to explore all the code paths in this function, what would we have to do? So first we would start with the input to the function, the x parameter, and we would have to model this specific type of variable, so a signed 32-bit integer in our symbolic execution engine. And that would help us. The reason I'm specific about saying it's a signed 32-bit integer is because integer math, you could wrap the integer around, you may be performing bitwise operations. To have a fully functioning symbolic execution engine, you'd want to model it fully. All right, so next we execute the code on our symbolic variables until we reach a branch instruction. And the first one is this x equals 0. And for each branch, we determine which values need to exist for that branch to be viable. And this is where SMT solvers come in. Often, actually, I guess you can have a symbolic execution engine without SMT solvers. I think all the ones I've seen actually always have them. Yeah, I know Klee uses it. Basically, all the ones I've looked at, they're paired together. And so as you reach a branch condition, you can update your current set of constraints that get you to that path. And so we're modeling the code. We know what the comparison operations are, and we build our constraints that way. One thing I didn't add in here is, say there's like an x plus equal 1, then you would also have to model that, add that to the constraints as well, and model that in your execution engine. All right, so we have a constraint and we know it's satisfiable. X can equal 0. There's nothing preventing that. So we fork. That's usually the method that I've seen them use. Once they want to branch and explore a new branch, they fork the current state. And if the path to the new branch is satisfiable, then it will set the new values to that and then continue down the new path. And so now we still have these current constraints being x equals 0. So the x's mean we've executed those lines. And so now we're on to the next one. So we have the constraints x equals 0, that's what got us here. And then now we see a new constraint, x is less than 0, which is unsatisfiable. You can't have x equals 0 and less than 0. So we don't fork to explore this first one. And which takes us to the second one, where we use the inverse of this condition, the x less than 0. And now that we fully explored that function, we start back at the top. And I tried to make this as simple as possible. There are optimizations you can do, but I think for demo purposes, this gets the point across. So we go back to the top and we have the sets of constraints that we used before, except we negate one of them. And that skips this branch and takes us to the next one. And we already added this constraint, so that's fine. And we end up going in here and we skip this one. So then again, you go back to the top and you basically perform all permutations of negating the clauses, or no, the expressions in your constraints. Conjunctions? No, I always blank on the specific terms for a piece of this equation. And so now we've got the negated ones. We skip this part, and this will not go into here. And now we'll go into this one. Now we fully explored this function. This is glossing over a lot of things. I did keep it high level, partly because I wanted to talk a lot more about the applications of this. And there is a big part that I did gloss over on this as well. So this is operating directly on the source code. Your symbolic execution engine will have to know what the source code is, what it's doing. So whether it's operating on the AST itself, or you compile it to an intermediate language and then operate on that, your symbolic execution will have to understand the code. Usually it operates on an intermediate language of some sort. All right, any questions about that? No? All right. So concolic execution, also known as dynamic symbolic execution, it's similar to symbolic execution, except that concrete values are used to gather the path constraints. So the concrete values won't change throughout the execution of the program while you're exploring the code. And concrete and symbolic values or variables may be mixed. All right, and symbolic execution tools. These are the few that I've known of and that I've known people using. CLE is one of the best ones. A lot of people use it. BAP, I don't know what CLE stands for, but BAP stands for Binary Analysis Platform. That one operates on its own intermediate language, the BAP intermediate language, and CLE operates on LLVM Bytecode. Triton, I believe, has also its own intermediate language. The guy who makes this is, I've been following him on Twitter for a long time, and he does a lot of really interesting research. I really like his tools. Anger is a somewhat recent one from UCSB, and Manticore is another one from Trail of Bits. And I think ranked in how old I think they are, this is how, with the newest ones are at the end of the list, as far as I know, or at least from when I became aware of them. And these three specifically are very heavily focused on finding security flaws in programs. These two also have tooling like that. I see these ones used a lot more specifically for those types of challenges. It's like reverse engineering things and automatically finding bugs, determining if they're exploitable, and possibly helping you perform exploitation of a program.
You mentioned that we are using BAP. Do you mind just sharing whereabouts we're using BAP and for the,
if I said, I didn't mean to say that. If I did say that, I've used it personally. I have not used it at GitLab. I've used it in previous companies.
Oh, my bad.
Yeah. All right, so CLE is one of the foremost tools for symbolic execution. It forks at each branch to explore different paths, and it uses the STP SMT solver. I think I may have gotten that name wrong, but it operates on LLVM Bytecode. So if you can compile anything to LLVM Bytecode, then it can symbolically execute it and explore the paths within that code. All right, so the sample function, if we wanted to explore it with CLI, you need to instrument it. So a lot of these, I guess what I would say more advanced analysis tools, they require instrumentation, they require a test harness to be set up, and it's not so much plug and play, usually. So with CLI, you need to instrument it. This is us calling that function, and we need to say this variable or parameter to the getSign function is symbolic. And Julian went over this last time. I wanted to briefly revisit it because it will make the next examples make more sense. And so this is running Clang or compiling it with Clang into LLVM Bytecode. This flag here, emit LLVM, tells it to emit the Bytecode for it instead of actually compiling it to an executable. So symbolic, oops, BC, there we go. File symbolic. Oh, I'm in a Docker container. File command's not there, but that's what it is. Oops, wrong one. All right, so now running, once we have the Bytecode, then you can just run CLI directly on it. That's this first command, CLI, symbolic CLI example.bc. And Julian mentioned this one too. There's the K-test tool that will show you the output of one of the generated inputs for the program. So the green part is it executing it. When CLI runs, it generates a series of folders. So you have CLI out 0. And with each of these being different inputs that cause, or that CLI used to explore your program. And so if we do K-test tool CLI last, this is where we see, okay, so the variable name was A, that's what we told it. Its size was 4, it's an integer, a 32-bit integer. This is the binary representation of the data, hex, and that's it, right? So 3 different branches. So it chose to use a very large integer for the second one. And for the third one, it used a negative integer. And if we go back to, keep doing that, all right. The example here, so we had x equals 0, which gets us to this one, and a negative integer goes down this branch, and a very large integer goes down that branch. So it explored all the different branches in the code, 100% code coverage on that function. All right, so how can we apply this to what we do here at GitLab? That was a big question at the end of Julian's presentation. There's a lot going on here. We're using SMT solving, symbolic execution, lifting code from its source code language into an intermediate language so that we can operate on it. There's a lot of ramp up time to be able to know what everything's doing and how to use those tools, especially if you want to do this from the perspective of GitLab, possibly adding it to like the secure stage or an extra CI pipeline, right? It would be a lot to try and do it automatically. So this came up with, let's see, using unit tests as a starting point ended up being a really cool idea that came up in conversations that I had with Julian a while back. We were talking about, I don't remember exactly what we were talking about, but in the context of using SAST and DAST on programs, sometimes you need to know how to run the program first before you can actually do more interesting things with the code. You can only get so far only looking at the code statically. It also applies to fuzzers. You need to be able to know how to run, build the program. So if you use unit tests, the developer has already taken care of setting up everything for the project. You know how to run the code. You know all of the dependencies. The environment is already set up because it's running the unit test. Now, if you run symbolic execution on top of the unit test, you get a few added benefits. You can boost code coverage. It would be relatively straightforward to instrument. Most projects use some sort of unit testing framework and most support plugins. And you can add hooks for framework specific conditions. So say it's Ruby on Rails application or Python Flask web application, you could check for specific things specific to the framework, like not allowing cross-site scripting, or maybe not writing to files outside of a certain temporary directory. So all of that is building up to this. This is the proof of concept I made. I called it PyTest Auto Explorer. It is for Python, and there's a reason for that, and I will talk about that in a minute. But it is a PyTest plugin that automatically explores the code using defined unit test as known good starting points. And the whole experiment with PyTest Auto Explorer was to be able to install the plugin and automatically boost your code coverage from your unit test. And I'm super happy to say it was pretty successful. It is limited right now, but here's a link for it. And we're gonna walk through using it. Oh, and here's my slide where I talk about that. But yes, this is using the unit test is, I like it a lot, and so far it's panned out. Again, keeping in mind that the goal is to not have the developer have to learn the details of SMT solving or fuzzing or symbolic execution. All right, so PyEXZ3 was a project I'd run across around the same time that we were talking about using unit tests to bootstrap analysis. PyEXZ3 is basically a symbolic execution engine for Python programs. And the way it does things is pretty cool, but it is I did not add it. Actually, I'm gonna show you some code. I didn't add it in the slides, but I meant to, and it's super cool. So it's a symbolic execution engine. It uses SMT solvers. Specifically, the one we're using is the Z3 solver, and it explores all the branches in the Python code. Now, the way it does that is, I think, pretty interesting. PyTest explore. There we go. So this is where PyEXZ3 implements its symbolic type. And the way it knows when a branch or the constraints that have been placed on the code or variables is it overloads the comparison operators of its symbolic variables. And I thought that was a super awesome use, very simple, and it works great. So if you have a symbolic variable, var equals, symbolic variable, and then you use if sim var equals 10. So say you have this code. In this operation, this function will be called, and this records the constraints that have been checked against the variable. So it actually performs execution or the comparison, but it also logs what it was being compared against. So as the Python code is executing, it can build these constraints based on the current execution of the code. Yeah, so it actually runs a Python code, replacing real concrete values with these symbolic ones so that it can capture the constraints and the path that it has gone down. Any questions about that?
Yeah, maybe
so
just oh, sorry.
Go ahead, Julian.
Yeah, just wanted to ask a short question about I mean, based on this overloading of the different operations that you have, is it also possible if you find, let's say, a function call to hook a set of SMT constraints that basically represent the semantics of this function call onto your set of constraints? because that would be great. You don't have to actually go inside a certain library or something. You could just pull the template, hook it into your set of constraints, and try to solve that.
That would be totally possible. I'm not sure. Let's see. Actually, no, you could do it. All right. Remind me when I start talking about instrumenting the functions. That's where I would do it. Yeah, I think you could store that information on the function object itself. So in Python, everything is a function, right? Or everything is an object. So a function is a function object. And you can add additional attributes to the function object. And so if you fully explored a function, you could store its, I guess, constraint tree on the function itself, so you don't have to, so you get that up front. That's what you're talking about, right?
Yeah, basically, yeah. Because I know that this is somehow a problem that's still kind of unsolved yet. So at the moment, what's usually happening is that you're going into libraries, and you basically, this is one of the reasons why we usually run into this path explosion problem, is because you're basically ascending all the time into other called code that's somewhere, and then you try to extract the constraints, and so your constraints is getting bigger and bigger. But if you already know the semantics of a certain operation, and if you have a template for that, it would be super cool if you could just take the template and avoid like ascending into called functions.
I think you.
By template, do you mean like
a
a predetermined path that's already determined for that library? So you don't have to do that?
Yeah, I basically mean that if you have like an operation that you could express with a basic set of constraints, instead of like going into this operation and collecting all the constraints, you could basically just
pull the template.
You could pull the template, yeah, and then
the template represents like a cached version of that actual run. Sorry, I cut you off.
Yeah, basically, yeah, that's true. Yeah, that was basically what I meant here. But that would be super cool.
Path have some canonical way we can represent that, you know, because I'm thinking of like, you know, if maybe this is getting too far into the weeds here in terms of details, but if you could represent the path as like sort of a key value, then each path exploration can be cached at some level, and so you can terminate having to explore the full tree each time, especially if like a lot of shared libraries are in use. Once, you know, we've analyzed one project and we sort of understand the path exploration for that library, being able to reuse everything from a certain layer down is probably an optimization in the future. If I understand what you're saying, Julian, tell me if I'm completely off here.
Yeah, no, that's one way of thinking about it would be caching, but another way would be also if we have like across libraries, you also have a lot of common functionality. You know, thinking about string libraries, for example, that you have for different languages, and if you, for example, have some upfront, some domain knowledge upfront about how certain operations are working, let's say string concatenation, you could basically have already a template for that prepared that's basically pulled whenever you observe this operation, and then you actually don't have to solve it for the first time because you already have a template at hand that would be usable across different languages, basically.
Yeah.
It sounds like that knowledge, that template becomes an inventory of templates that you can pull on the fly to potentially remove the need for runtime calculation, because we've already figured it out.
Yeah, well, and that suppose you had that for like everything, then you wouldn't necessarily need to do framework specific things because you know all the details about the framework, instead of knowing that say like a web framework like route.write writes to a WebSocket, that would have been fully explored and you may not need to do the framework specific things. Interesting. So it's there's a lot of overlap there with the unified SAS things that we've been talking about too, caching abstract syntax trees and representations of code. Yeah.
There was something you said, James. I just want to make sure I understand. So like from the developer's perspective, they were able to go write code as they would. And the tooling that we provide here would be sort of transparent to them. It'd be minimal in terms of being able to inject so that it can then explore the different paths that the developer may not have considered
Yes.
of that code. And that's why,
or that were maybe too tedious to add. So like 100% code coverage isn't always a goal, because it takes a lot of work to get that last like 5%. If you had a very robust symbolic execution engine or something that automatically explored your code, you could probably get 100% without having to do all the tedious work yourself.
And the benefit to the developer is you don't have to do the tedious work. You get this knowledge of like, here are the hotspots you may want to focus on. And it requires very little investment. The investment is to, in this case, it was PyTest Auto Explorer as like the additional package to include. And it was unobtrusive for the most part from.
Exactly.
Okay.
And I'm going to, so PyTest Auto Explorer is the proof of concept that I made. And I was surprised at how, I guess, relatively straightforward it ended up being. There weren't any huge snags anywhere. But yeah, I'll get a bit more into that. Yeah, so taking a step back a little bit, PyEXE3, the reason why I use Python for my proof of concept is because I'm building on top of PyEXE3. And so some of my proof of concept's limitations are because of limitations within this proof of concept. They are overcomable, or they can be overcome. I don't think overcomable is a word. They can be overcome, but they are there right now. It's a proof of concept. So the big one is that PyEXE3 only operates on integers. So it uses SMT solvers. It works with symbolic values, but only integers. And now everything like SMT solvers support string theories. So Julian talked about different theories with SMT solvers. They support strings, regular expressions, but that would have to be added in. I don't think it would be too much work, but it's just not there right now. All right, so with PyTest, this is PyTest is extremely straightforward to write tests for. It's one of my favorite testing frameworks in any language I've ever used. You don't even have to import the PyTest module. You just have to have a test function, or a function that starts with test underscore. And you use assert to assert different conditions. And PyTest takes care of everything else. So as an example, this is running the previous code. And there we go. That is it. All you say is use the PyTest command on your code or point it at a directory. And this is actually telling the coverage PyTest plugin to only do coverage on the test sample module, which is just our code, right? So now we covered 100% of our test code, which makes sense because we ran the test. But yeah, that's as simple as that is. And PyTest has a very robust plugin API that lets you hook most aspects of running tests. And so PyTest Auto Explorer hooks functions within test cases themselves and performs either concolic execution or fuzzing on the identified function calls. So it's kind of a bonus that I tossed in. Since I'm instrumenting the code and hooking all of the functions, we know the input variable or parameter types, their initial values. We could also do fuzzing in the same pass, which is why I called the plugin Auto Explorer and not SMT or like Symbolic Execution. It's just automatically exploring your code. All right, so I made a very simple test project. It's in the examples directory in PyTest Auto Explorer, and it does some basic math operations, only adding and division. We don't care about multiplication here. All right, so again, very simple, but they are buggy. They do weird things, right? So if the number is dead beef, we're writing to a file for some reason, right? Otherwise, we just return this. And same with division. we're doing unnecessary things everywhere, manually raising an error. We're returning a non-numeric value if a number is 1337. Weird things about the code. Maybe this is old legacy code and somebody inherited it, right? All right, and the test project also has some very basic tests. So this one just calls the function. If there's an exception that was raised, then the test would fail. So this is basically just making sure there's no exceptions raised while running the tests or calling the functions. And this is performing some minimal tests on the return values of the functions. So abs divide needs to return a float. And this one tests that no files should be written when using the add operation. Like, well, it should never happen. So the developer has the test there, but it's actually not catching the test. So out of the box, without using the plugin, it's got 68% code coverage, which isn't great. I personally would want to see that a lot higher. And those tests are not very robust. They're not exploring all the paths in the code. So now we're going to talk about actually using PyTest Auto Explorer and a bit about how it does the hooking and exactly what it's doing. So the requirements to be able to use it, all you have to do is install it and then rerun PyTest and add -- autosolve, and that's it. And then it instruments the code and automatically explores all the paths in your code for integer values. All right, so here we go. We are going to do PyTest cov test. Oops. What do I have? Oh, all right. There we go. PyTest cov test project. So this is telling the coverage plugin to only record code coverage for the test project module. If we don't do that, it'll do code coverage for all of the built-in Python modules, everything, and we don't care about that. So we'll say auto solve and test. Oh, oops. Test project tests. There we go. And suddenly we've got code coverage boosted up to 94% instead of running it without it. We've got 80%, which doesn't seem right. Oh, I modified something. Dang it. Then test project test. Did I? Okay, maybe that. No, I didn't add it. Okay. Huh. So I think I added a new test after I made that slide. So 68% was the wrong number. It's at 80% right now. All right, so let's do this. Oh, okay, I know where that number came from. Test project. So now if we do it, it was including the test code itself, which boosted the number.
Do you need to go test project / test project for the cov, or CD into test project?
CD, yes, I just CD'd into test project.
Oh, I see that. Okay,
Yep.
Sorry about that.
Oh no, you're good, you're good. And just test. There we go, there's the 68%. All right, so the boost we're getting, adding autosolve, now we're at 100%. There we go, 100% code coverage just by installing the plugin and saying autosolve. Now all this extra output, I don't know how to get rid of it. I'm not sure where it's coming from. So that would be a to-do. But you can see here, we are actually getting a bunch of errors. I don't know if you noticed. So initially we have 3 tests. When we run it, we have 23 tests. And that's from automatically exploring the code and instrumenting the test functions. So these are solved cases. This one is specifically for the test add function. I'm going to make this slightly smaller than test basic, test add. All right, so that's testing this function, right? And it says if the number is this number here, which is actually that test project. All right, which is actually dead beef. So if num1 is dead beef, then it raises this exception: math functions should not be opening files, which was the original intention of the developer, was to make sure that it's not opening files, except he wasn't passing in dead beef, or the developer, not necessarily a guy, was not passing in dead beef. So we found that one. Now these other ones, so you get the arguments or the parameters to the function that it was called with. And so abs divide should always return a float. It returned special, so it found that one. And this one here is the explicit divide by zero exception, which was explicitly raised. We add test project divide. That was right here. And again, this is just a slightly different code path to get to the same thing. So it hit an extra branch getting there, which is why that one showed up. And this one is a different variant of the divide by zero exception. But yeah, you can see all of these are awesome. And you get it just by installing the plugin. Before I go into details about its implementation or continue on, does anybody have any questions about this so far? No? All right. Cool. Now let's do the next part. So the way PyTest Auto Explorer works uses Python's runtime introspection to determine function arguments. And depending on the type of arguments the test function has, it may either directly instrument the Python bytecode itself or wrap the test function and solve the wrapped function. And there's a pretty big distinction between the two. Directly instrumenting the Python bytecode of the function means that within a single function, so let's go here. So say, for example, within this function, it will instrument this function call specifically. And then here it will instrument that function call. It's not instrumenting this entire thing. So that's the difference when I mean it's wrapping the function versus instrumenting it. All right, so Python bytecode is something I need to explain before I can really talk about how I'm instrumenting the Python bytecode. So Python bytecode is similar to other forms of bytecode. It's very simple. It operates on a stack, or it has a concept of a stack, and it has variable names that it stores, and most of the instructions are pushing to the stack, popping from the stack, or grabbing a variable from the variable store based on an index. Yeah, it's not too bad at all. You can see what Python bytecode looks like. There's a built-in Python module called dis for disassembly. You can give it a code object or just a raw string, and it will show the disassembly of the code. I mentioned before that Python functions are objects. They're function objects. Every function object has a dunder code attribute. So dunder means double underscore. So double underscore code, and that is the actual code object, the compiled bytecode of that function. And this is what that function looks like. And these indices are arguments to the instruction itself. Sometimes they reference an index into the variable store, or number of parameters is specific to the argument or to the instruction. All right, so simple test functions that do not declare keyword arguments, each function call that calls into the current project is replaced with the custom callback. And the callback captures the original function, the positional arguments, and the keyword arguments that were being sent to the function. And at that point, we have full control to do whatever we want. We can run it like originally, just run the function and pass in the provided arguments, or we can do whatever we want with it. Fuzz it, do SMT solving, sky's the limit. What time is it? All right. So for example, this is a function call. It loads the name some function, passes in 2 parameters, 1 and 2, and then calls the function. The call function instruction, the argument for it is the number of parameters. So it pops that many parameters off the stack, and then what's left on the stack would be some function value, and then it calls that function with those parameters. So after instrumenting it, this is what we have. Very similar setup. It loads the function, puts that value on the stack, puts these 2 constants on the stack, the parameters, but then we cache the positional arguments, the keyword arguments. There are none, so it makes an empty map dictionary, and then it stores the original function itself in this temp function variable. And then it does some things here to load the sys.function callbacks object, and it uses this key to look up the callback, and then calls that callback from sys.callbacks with the cached or temp argument. And at that point, that's where we are fully into our code, and we can do whatever we want with the function. And this is, there's no magic value here. It's, I didn't add this to the slides. When it does the hooking of the function calls, it assigns it a unique identifier. And then, so sys.call fn callbacks is a dictionary, and the keys of a dictionary are the identifier, the values is the callback. It's just an easy way to access the callback, because there's not much state persisted in here. That would be easy to, it's not easily accessible from the Python bytecode. All right, so that was for simple functions. For functions that declare keyword arguments at the top, which is not normally something you do in Python tests or PyTest functions, but if the developer does that, then we could just wrap the function itself and solve this function. What that gets us is that the developer can add custom air condition checks. So then it becomes more of a real unit test. Then we're running the full unit test with all of the different possible values for these declared arguments. Any questions, comments about that before I keep going?
How are we going about what values to pass into the test function?
Okay, so that is a good point. So one of the things that I liked about using this mechanism, just keyword arguments with default values, the default values become the default, right? And if you're doing SMT solving, then it knows the type of the value. You could also use Python type hints, but I didn't add that in here. But yeah, it gives you the type of the parameter, a default initial value, and it's a good starting point. So how does PyTest AutoExport know what values to give it? If you're doing solving, it does SMT solving to figure out what the values need to be to go down certain paths. If you're doing fuzzing, it just depends on the fuzzing mutation algorithm you're using, right?
Yeah, that makes a lot of sense. Thank you.
Yeah, no problem. All right, so a quick bit about fuzzing. I kept this super simple. The code base for Python AutoExport only operates on integers because of PyExe3 limitations. The fuzzing aspect is not limited by that, but I just kept it simple, and it's also only integers. And I didn't go crazy on it, implementing fancier fuzzing. All it does is, for all known integer arguments to whatever's being instrumented, it tests all permutations of those arguments with the range -20 to 20. And this could very easily be expanded. Actually, since I'm in here, where is it? Oh, that's right. Here we go. So this is the fuzzing function. And this is actually from the instrumented code, whether it's wrapped or directly swapped out. in the Python bytecode, you end up getting the original function, the args, the keyword arguments, and this is a few extra things that you get. But yeah, this is where it's doing the fuzzing. So here it's actually calling it, and here it is doing all combinations of this range for this number of arguments. And then it assigns them and does its thing. And if there were any exceptions raised, then it catches it and logs the test case. So relatively straightforward. All right, so now let's do the same PyTest thing with examples test project PyTest. All right, so this, PyTest test. Here we go, 68%, and now let's only autofuzz. Then we get up to 84%. But since we are only, oh, and you should notice we are testing many more test cases now, all permutations of the range -20 to 20 across n number of arguments. So that's what, 1,600 test cases. And we have a lot of failures. So it hit failures. Oh, whoops. That is, I thought I fixed this. This was a bug in my code. It shouldn't have been that many failures. I was going to say. Well, demos, live, and presentations. But it's fuzzing. And let's test basic. Let's just comment that out so we don't have to deal with that. All right, so now if we run it, we're not going to have that error. So now we're hitting divide by 0 exceptions and different things. So 800 passed, 23 failed. This is more about what I was expecting to see. And again, didn't have to instrument the code at all. We are close to running out of time. All right, so let's keep moving. So if you did want to explicitly say, I want to auto explore this function, I did add a decorator to the PyTest auto explore code. So on a test function, you could say explicitly auto explore this, and it will do it. You don't have to add the -- auto solve or auto fuzz. Now, things this gets you is that you don't auto solve or auto fuzz all tests. Maybe you don't want to do that. It could be very expensive. Maybe there's only certain areas that you want to focus on. But then it also lets you set certain options and be way more specific about what you're doing. But it does require setup by the user, which is what I was trying to avoid with this whole proof of concept. So this was an afterthought, but it is useful. Now, we talked about mixing symbolic and concrete values. You can do that with the auto explore decorator. If you use the decorator as a function, as in you call it first, then you can set the symbolic values and the concrete values. Concrete values are never changed. They are passed verbatim throughout the program while executing. So yeah, that lets you do more complicated setups. PyTest Auto Explore also does some smarter detection in the, so for example, here, we have num1 and num2. These are integers, but this mocker object, that's a PyTest specific thing, and it's a mock object. PyTest Auto Explore knows it can't handle it and automatically makes it a concrete value instead of a symbolic value. So there is some automation going on there, but you can explicitly set these things as well. Another thing you can do with this is you could say explicitly turn off solving and only fuzz, or you could say fuzz equals true and the default is to solve, so then you'll be doing fuzzing and solving on your test function. But yeah, that is, I think we are just about out. Yep, that's about it. Any questions? Want me to go back to anything, explain something else?
I was curious if you are aware of Hypothesis and that library.
I have seen it. It's been a while since I looked at it. That is where you, let's see, you decorate your functions with what it's expecting basically the function contract, right? And then it tests that, right?
Yeah, it takes kind of a property testing approach where you can set up the properties and the different values that you might want, and you can limit the range, etc. But what's interesting about hypothesis too, I used it quite a bit in Python, but they've also been working on expanding it to other languages. So there's a more common DSL for property testing across other language stacks, which is pretty interesting, especially when thinking about figuring out how to maybe apply some of these concepts automatically to someone's code base. One thing that I really liked about hypothesis approach is that they actually store failed examples in a directory, so that you have like that. What do you when you fix a bug or whatnot? You have that regression test. So that's pretty useful too for. And I don't actually know. This is probably a really clear question. What is the difference between fuzz testing and property testing? Is there a difference, or is it just two names for kind of the same thing?
So, I don't know. Fuzzing is not security specific. You're generating inputs and sending it through the program. How smart you get with it depends. I think, as far as I know, they could be the same thing. It's maybe there's something more specific about property testing that I don't understand, but my understanding is that they're pretty much the same thing.
That was kind of my understanding too, so I was curious if there was something I didn't know about there. So
yeah. Oh, that was another thing that I wanted to mention. So here in this example, we are still sharing my screen. Yeah. We're making sure it doesn't open any files, right? Math functions should not have to open a file. I didn't add this into the example, but since we're instrumenting this whole function, we could add our own mock things to test for certain conditions, whether they are security related or not. You could build that into the plugin itself, so you don't have to add this in the test code. And so you just have this assert is instance blah. And then the plugin itself would have a whole suite of additional checks to check for. So if it was a Flask application and we were using string theories with the SMT solver and everything supported strings, then we could test for like cross-site scripting or something. Yeah, so there's a lot of having the initial code instrumented and having yourself plugged in gives you a lot of flexibility in what you can do potentially in the future. Again, this is just proof of concept. It's not super robust. It's only numbers, but it's interesting.
Another question I have is, one of the things that came to mind when you were talking earlier about that last 20% of test coverage and how it can be really hard won. A big part of that is dealing with codes that have side effects, right? And like, well, now I have to set up the world, or I have to and not do it in this like very fragile way. And one of the things that I think is really cool about symbolic execution and some of these other approaches is that you don't necessarily have that same side effect problem of like, it can look at the code, it can think through it, it's not executing your code necessarily directly, so you don't have those side effects. Worry about RFing the root of your driver or something. But in your case, I think, are you actually executing these test functions or the functions within the test function, so you have to worry about that?
It is actually executing it. It is catching exceptions, but it is not. Well, and this is where let's see, Julian probably has a lot more insight, but it depends on the implementation of the execution engine itself. It's like CLI operates on LLVM Bytecode. This PyEXE3 execution engine that I'm basically wrapping actually runs the Python code itself, but uses symbolic values during execution. So it's concolic execution. Yeah, so it's, in my case, it's not emulating it. It is actually running it, yeah.
Perfect. So that's kind of the distinction between concolic and symbolic. I missed the very beginning. I was planning on watching back.
Okay, so yeah, Another word for concolic execution is dynamic symbolic execution. So if you see, skip through all that stuff.
I can watch the front.
Yeah.
I'm sorry.
Oh, there we
Sorry
go.
about that. Yeah.
No, that's fine. Yeah, so it's using concrete values during your runs
Oh,
is
interesting.
what makes it a concolic execution. Now, I will say I've done a very proof of concept implementation of a symbolic execution engine in the past, but my experience with them is mostly knowing a decent enough to use them and know how I can use them and when I can apply them. But my expertise in it is not, I wouldn't call myself an expert. I know how to use them though. Yeah, so terminology wise, I think I'm on point. Yeah.
Nice.
Yeah. Yep. And yeah, that's about it. Any other questions? Does anybody want to see any other examples, specific ways things were implemented? Anything?
Yeah, I'm kind of curious about because you illustrated fuzz testing and also symbolic execution. I was wondering,
Yeah.
the different types of bugs or issues you discovered, were there a large overlap, or were the kind of issues different with both approaches that you've been using?
So that is a very good point. So fuzzing is only as good as your mutation engine and your feedback. So feedback-driven fuzzing, I think the general case, you should consider all fuzzers feedback-driven, and really dumb fuzzers just have a no-op feedback mechanism. But really, a fuzzer is only as good as those two things combined. So if your fuzzer knows if a new test case has explored a new code path, then it could mutate on top of that test case to hopefully explore further into the code path, right? Or new code paths past that one. The sample fuzzer that I have in this does not do that. So Julian, you were asking about overlap. Because the fuzzer or the mutation engine I gave the fuzzer is extremely basic, it only tests the ranges -20 to 20. It will not find those values where it's checking for like 1337 or dead beef. It just won't find them because it's not even coded to do that, right? So auto fuzz, here we go. So we have, it did find divide by zero exceptions. We went from 68% up to 84%, but again, we're not getting those other higher values because we're just not testing it. Yeah, and that is a big difference where in the overlap there, fuzzing can potentially go a lot faster. So that we're doing over 800 test cases in 0.13 seconds. For Python, that's not bad. And let's see. This won't really be a good example. There's a lot of setup time. But just for doing 20 test cases, we're already at 0.2 seconds, right? So that's one of the big distinctions or benefits of using a fuzzer is that they can be really fast. And a lot of times extreme performance will beat any amount of smarts. Yeah, with interpreted languages, the difference isn't quite so big. If this was C code we were instrumenting, the difference would be exponential. It would be extremely dramatic. High performance fuzzers now, so one of the guys I follow on Twitter, I love his work. He's constantly trying to improve fuzzers, and he wrote his own RISC emulator that uses vector instructions on Intel processors, and he's getting like 100 million test cases per second fuzzing the C tags program. And like 100 million per second is insane for anything interpreted. Like there's no way you can get there. So yeah, it's that's just a sample of the difference between the two. Fuzzing can be very high performance, and then you just brute force your way through it. You mentioned Oh, I think you dropped off. It was mentioned that the test cases could be saved off into a file. I did think about doing that. I've seen another PyTest fuzzing plugin do that, but I didn't do that for this. Yeah, that's always an interesting one. Like, do you want to add that into CI and like add the test cases back into the code? And it just seems weird committing back to your own repository from CI. But yeah, that's something you could do. All right. Last things, the CLI is, here's a few links. There's the homepage. I was using CLI in a Docker container. Here's some good documentation. This slide had a pretty good overview of symbolic and concolic execution. And this is the tool I was using to present this presentation. I like to do things from the terminal, and I wrote this, and it's just marked down, rendered in the terminal. So
it's amazing. I liked how it had the little terminal inside your presentation before
yes.
the Docker shell. That was cool.
Yeah, no, it's I could do a separate, I could talk about this tool for a long time. I like it a lot. It has a lot of benefits. Long story short, here, I'm just gonna pause the recording. Stop, where's,